Okay, hi, so welcome to the video where I go through the full Chemistry Unit 2 paper. That's for AQA Chemistry, and it's the higher paper for Unit 2. And this is the June 2013 series, which was sat on May the 20th, 2013. Now, I was going to do the 2015 paper to start with, but for one, it's quite hard to get hold of, and for two, all the reports said that it was really easy, and so this one is probably more useful to you than the 2015 one. So this is the higher paper. If you're doing foundations here, some of this won't apply to you, but we're going to go through every question step by step, and feel free to pause, rewind the video, so you can go at your own pace. But let's go straight ahead on to question 1. Alright, so question 1 says that some students did an experiment to find the temperature change when hydrochloric acid reacts with sodium hydrogen carbonate. Alright, and so you've got this thermometer, you've got the spatula, and you're putting in the sodium hydrogen carbonate into hydrochloric acid. Right, and we've got the results here in the table. So the number of spatula measures of the sodium hydrogen carbonate, and that's down the side. And you've got your starting and your final temperature and your temperature change in the final column. Alright, and we can see straight away that the temperature change of 10 degrees doesn't change as we add more and more sodium hydrogen carbonate. So that is likely going to come up in the question. Alright, so let's move on. It says describe as fully as you can the trends shown in the students' results. Alright, so straight away that's what we're going to do. And so importantly, it says describe, it does not say explain, so we're not going to explain why the trend is what it is. All we need to do is describe what we can see. So let's go back again. What we're going to say is that the change in temperature we can see increases as we increase the number of spatulas of sodium hydrogen carbonate. That is until we get to 8 spatulas, because then the temperature change is 10 degrees Celsius, and after that it doesn't change. Alright, and so that's basically what we're going to say. I'm going to say that more sodium hydrogen carbonate added causes a larger temperature increase. Alright, full stop. The next point is this happens until 8 spatulas are added. Okay, after this, I'm going to say after this amount so that we are being specific. So after this amount of spatulas added, the temperature change is constant at 10 degrees Celsius. Alright, and so that's 3 marks. That's more than enough. We've described the trend, and so we are happy. Let's move on. I'm going to use a slightly thinner pen because the handwriting obviously isn't very good. So in part 2 it says state the type of energy transfer for this reaction. So when it says type of energy transfer, we're talking about exo or endothermic, right? So if we have a look, the starting temperature is always higher than the final temperature. So the temperature is always going down, right? So as you add more sodium hydrogen carbonate, temperature change is greater, and so the temperature goes down more, right? If the temperature goes down, it means that energy is taken in from the surroundings, and this is what happens in an endothermic reaction, right? So I'm going to say endothermic energy transfer, right? Just having the word endothermic would have got you that 1 mark, because it's only a 1 mark question. Alright, so let's carry on. In 1b it says that sodium hydrogen carbonate is used as baking powder for making cakes. When the cake mixture is baked, the sodium hydrogen carbonate decomposes. The equation for that reaction is, and it shows below, you've got the sodium hydrogen carbonate on the left, right? That makes sodium carbonate, right? Obviously the hydrogen's left from there, plus water plus carbon dioxide. The cake mixture rises when baked. Suggest why. Alright, so we're going to use this equation to suggest why. and it's only 1 mark. Well, if you think we start off with baking powder, which is a solid, and at the end we produce a solid, but we also produce 2 gases. Those gases are water, which will be water vapor or steam, and carbon dioxide gas. And now the gas obviously is going to expand and it's going to leave, and that will cause the cake to rise because it will create air bubbles within the cake, and that's what you see, and that's why cake is crumbly. So what I'm going to say is that gas is produced, causing cake to rise. Alright, you could have been specific and said that CO2 or H2O gas is produced. Either of those would have been fine, but for 1 mark, that is more than enough. So, B part 2. It says the same reaction can be reversed to produce sodium hydrogen carbonate from sodium carbonate. So it's the same thing the other way round. Now, this is actually quite a tricky question because it says, do the reactants need to be heated, and give a reason for your answer. Now, if you have a look at the mark scheme, you could have got the 1 mark here. It's only a 1 mark question. You could have got the 1 mark for saying yes or for saying no, right? And that sounds a bit weird. But if we go back, then you'll remember that this is an endothermic reaction, right? So when sodium hydrogen carbonate breaks down, we can say it's an endothermic reaction. And that means that forming sodium hydrogen carbonate is going to be an exothermic reaction, all right? That was the wrong thing I showed you there. The equation for it, because we're not adding acid this time, the equation is sodium hydrogen carbonate plus heat. So it still is an endothermic reaction, but it's not the one where we're adding hydrochloric acid. So you can see that creating sodium carbonate from sodium hydrogen carbonate is going to be endothermic because we supply heat, right? And now, do we need to heat on the backwards reaction? We can say no, because the forward reaction here is exothermic. Right, exothermic. So because it's exothermic, energy is going to be released into the surroundings, and so we don't need to provide heat energy, right? Now, the reason I said it's confusing, and the reason that you could have got the answer for saying yes, is because most reactions require heat to provide activation energy, right? So I could have also said, I'm going to put this in brackets, I could have also said yes to provide activation energy. Alright, so quite a broad question. I would have preferred it if they had have told you whether you needed to supply an activation energy. If they'd have said no, then you would have had to have said no, you don't need to heat it because the forward reaction is exothermic. But as it is, you could have said yes or no as long as you backed up your answer. Alright, so that was a long time spent on a 1 mark question, but I thought it necessary to explain what's going on. So, question 1C, it says calculate the relative formula mass of sodium hydrogen carbonate. And we've got the relative atomic masses, and so in this case, all we need to do is add them together. So, sodium is 23, right, and we've got 1 sodium. Okay, and we're going to add to that hydrogen, which has a atomic mass of 1, and we only have 1 hydrogen. We're also going to add to that carbon, which has an atomic mass of 12, and we've only got 1 of those. And we're also going to add oxygen, but it's O3. So it's going to be add O3, which means that it's 3 lots of 16, which is 48. All right, and so I've written those the wrong way, haven't I? Let's put the numbers in here, and let's put the letters on the top, like that. Okay, so we're going to add those numbers together, right? And that is going to give us an answer of 84, and 84 is going to be our relative atomic mass, like so. Right, then it says calculate the percentage by mass of carbon in sodium hydrogen carbonate. All right, so what we're going to do is we're going to say, well, how much in terms of mass of carbon do we have in that sodium carbonate? Well, you can see that we've only got 1 carbon, so it has a mass of 12, and it's a mass of 12 divided by, what's the total mass of sodium hydrogen carbonate, is 84, right? Because that gives me the fraction of carbon over the whole thing. And then to turn a fraction into percentage, we times by 100. That will give us a percent, and our answer is going to be 14.29, and that is percent. So you do that in your calculator, your answer is 14.29. Alright, and that is the end of question 1. Alright, so let's have a look at question 2. It tells us that a student investigated the reaction between magnesium and hydrochloric acid. Alright, so we have magnesium plus HCl makes this salt, magnesium chloride, plus hydrogen. And it says state 2 observations the student could make during the reaction. Now I've put a ring around the magnesium chloride to start with because I want to point out that the state symbol for magnesium chloride is aqueous, which means that the only thing that's a solid here is the magnesium. So the first thing that we're going to see is we're going to see that magnesium disappears. Right? You could say dissolves, and that would get you the mark as well. But I'm going to say disappears because it's not the magnesium itself that dissolves, it's the salt that dissolves. Because magnesium chloride is aqueous, it goes into solution and we have no solid left. Alright, so what's the second observation? Well, I've drawn an arrow here. You can see these bubbles. Now those bubbles are as a result of hydrogen gas being formed. And so we're going to see bubbles. And the more scientific term for producing bubbles or fizzing is effervescence. Effervescence. Alright, and that's more than enough for 2 marks. Okay, so 2B, we're told straight away that we're going to be assessed for our use of English. And so we need to make sure that we're writing in full sentences and we've done everything in order. So it says the student investigated how the rate of this reaction changed when the concentration of hydrochloric acid was changed. Write a plan the student could use. And in the plan, we should describe how we'd carry out the investigation and make it fair, and describe the measurements that we would make. Alright, so basically what we're going to be doing is we're going to vary the concentration of hydrochloric acid. So we need to make sure that we repeat the test for various different concentrations of the hydrochloric acid. We also need to think about what are we going to keep the same, and certain things we're going to keep the same include the amount of magnesium. They also include the amount of acid. Alright, and so therefore that would make it a fair test. If we used a load of acid at a low concentration and then a tiny amount of acid at a high concentration, then we haven't quite made the test fair. So the first thing I'm going to say is that in the experiment we add a known mass of magnesium, and I'm also going to put known surface area, right? Because surface area is also something that can increase rate of a reaction. Known surface area into a known volume of HCl. Right, and so that's actually a fair few points in one bullet point. So we're going to be adding magnesium into hydrochloric acid. That's 1 point. But the fact that I've said that we know the mass of the magnesium, we know the volume of hydrochloric acid, and the surface area of the magnesium means that I'm taking precautions to make it a fair test. Alright, and so what are we actually going to measure? So we're going to measure the volume of gas produced and the time taken. So what we're actually going to be plotting is the amount or the volume of gas versus time. Because if we produce more gas in a shorter space of time, it means the reaction has happened quicker. Alright, so that's actually what we're going to be measuring to give us an indication of the rate of reaction. Okay, and then finally we are going to repeat experiment with various concentrations of HCl. Repeat each experiment, right? So each experiment at each concentration 3 times and average the results. All right, so if we accidentally measure something wrong or we're not 100% sure, that would mean that there will be error in our results. So what we're going to do is we're going to take averages over more than one experiment, okay, where we repeat exactly the same thing. So at each concentration we repeat the same thing, and then we are more confident that we have valid results. Okay, and that would be more than enough for the total 6 marks, as long as we wrote that in sentences rather than just bullet points. I've written it in bullet points to make it clear, but in sentences that would be perfect. Alright, so question 3 says ammonia is produced from nitrogen and hydrogen, right? We knew that. The equation for this reaction is shown below, and we've got that here. A company wants to make 6.8 tons of ammonia. Calculate the mass of nitrogen needed. Alright, now we're not going to convert tons into grams because then you'd be dealing with huge numbers and there's no need, because we want the answer in tons. So what we can do is just pretend that tons are grams and do the calculation just using small numbers. Alright. So if we want 6.8 tons of ammonia, then we need to work out how many moles that is, okay? So what I'm going to do is I'm going to work out using the equation N is equal to M over MR, right? That's number of moles is equal to mass over molar mass, the number of moles of ammonia, okay? Because I know I want N, but I know M and I know MR, okay? So the mass, in this case, and we're using tons for mass, is 6.8. And the molecular mass is going to be, well, it's 1 nitrogen, which is 14, plus 3 lots of hydrogen, which is 1, making that 17. All right, so we do 6.8 divided by 17, and that will give us our number of moles, and that comes out at 0.4. So that is equal to 0.4 moles. All right, now what I need is I need the molar relationship between ammonia and the nitrogen. So nitrogen here, okay, there's no number in front of it, so obviously we take that as being the number 1. But ammonia has a number 2 in front of it, which means that it's a 1:2 ratio. So I'm going to say 1:2 ratio, which means that if we have 0.4 moles of ammonia, well, it's 1:2. If this is 2, then we half that, making 0.2 moles of nitrogen. All right, so nitrogen now, I'm going to put this in brackets here so we know we're talking about nitrogen. And we use the same equation. N is equal to M over MR. This time, though, we don't know the mass. We do know N and we do know MR. So I'm going to say that 0.2 is equal to the mass, which is what we want, divided by MR, which is, well, nitrogen is N2. So it's 2 lots of 14, making 28. All right. So then I multiply that by 28. So M is equal to 0.2 times 28. That will give me 5.6 tons. All right, so you multiply out the 28 with the 0.2 and you get an answer of 5.6. And so 5.6 is my answer. All right, let's move on to the second part. The company expected to make 6.8 tons of ammonia, but they only yielded 4.2. Calculate the percentage yield, or the percentage yield. So percentage yield is equal to actual, let's neaten this up slightly, actual divided by theoretical amount times by 100. So let's just sub in numbers. What was the actual yield? It was 4.2, right? 4.2 tons. And the theoretical amount was 6.8 tons. 6.8 tons. So we do that sum, and then we times that by 100, and we'll end up with our percentage. And if you do that, you end up with an answer of 61.8%. All right, 61.8, and that's rounded to 1 decimal place. Okay, Let's put that percent sign in there. There we go. Now part 3, use the equation above to explain why the percentage yield of ammonia was less than expected. Okay, so let's go back up to our equation. Now, let me just rub this stuff out so we can see it a bit better. Now, on this equation, the important thing to note here, because we don't have any figures in terms of exothermic and endothermic, etc., what we can see is this. This arrow, double-headed arrow, tells you that the reaction is reversible, and so it's not all going to go one way. Okay, and so our answer is going to be that the reaction is reversible. Okay, so it's only a 1 mark question. Saying the reaction is reversible is completely enough, okay? Some of the products will, or the product, which is ammonia, will re-react and form the reactants, all right? So we're not going to get 100% yield. Okay, that's more than enough. Let's move on to part B. It says complete the dot and cross diagram to show the outer shells, or the outer shell electrons are below. Okay, so we use dots and crosses to represent electrons. Now the first thing we need to do is we look in our periodic table, okay, and I'm just going to tell you that hydrogen is in group 1, and nitrogen is in group 5. That tells you how many electrons they have in their outer shell. Okay, so nitrogen has 5 electrons and hydrogen has 1. Now hydrogen, because it's in the first period, only needs 2 electrons to be happy and have a full outer shell, whereas nitrogen needs 8 because it's not in the first period, it's in the second period. All right, so we already know that there are 3 hydrogens and 1 nitrogen. Each hydrogen is going to be happy with 1 extra electron. So I'm going to draw the hydrogen electrons as crosses, okay? Like so. And they need to share 1 with the nitrogen to become happy. So nitrogen I'm going to draw with dots. All the hydrogens there are completely happy. They all have 2 electrons in their outer shell now. But nitrogen here, we've only added 1, 2, 3 dots to this diagram, and nitrogen has 5 electrons, and so I'm going to draw the 2 extra ones up here. And now nitrogen also has 8 electrons in its outer shell, and that is perfect. All right, 3C. It says that ammonia dissolves in water to produce alkaline solution. Which ion makes ammonia solution alkaline? And any ion that makes a solution alkaline is the hydroxide ion. Hydroxide ion. And I'm going to put the chemical symbol is an OH minus. All right. Next one. Name the type of reaction between aqueous ammonia and an acid. Well, a reaction between an alkali and an acid produces a salt and water, and it is a neutralisation. Neutralisation reaction. Part 3, it says name the acid needed to produce ammonium nitrate. Now the important thing there is nitrates. That is going to come from the acid. So ammonium comes from ammonia and nitrate comes from the acid, and so it must be nitric acid. Nitric acid. Nitric acid produces nitrates, hydrochloric acid produces chlorides, and sulfuric acid produces sulfates. Alright. Part 4, it says the reaction of ammonia with sulfuric acid produces ammonium sulfate. Use the formulae of the ions in the chemistry datasheet and you can write the formula of ammonium sulfate. Alright, now ammonium is an NH4 ion and it is a positive ion. It is positive 1 charge. Sulfate, if you look, is SO4, but it is a 2- ion. Now, in a salt, the charges must cancel out, and here they don't. If I just added one of these to one of these, the charges don't cancel. You'd have +1 minus 2 will give you an overall -1 charge. So what we need to do is we need to have 2 of these, right? With 2 of these, I'm going to write below, times 2. Because 2 lots of 1 make 2, and then take away 2 would be neutral. So our salt is going to have 2 ammoniums plus 1 sulfate. And the way we write that is the ammonium, NH4, and then we want 2 of them, so we group the whole thing and we write a 2, and we only have 1 sulfate, so we don't need brackets for the sulfate, and we just write SO4 after, and that is the salt ammonium sulfate. Okay, and that is the end of question 3. Alright, so question 4, it says that this question is about potassium. Good to know. Now, Humphrey Davy was a professor of chemistry. In 1807, Davy did an electrolysis experiment to produce potassium. Davy first tried to electrolyze a solid potassium salt to produce potassium. Explain why this did not work. Well, an electrolysis is when you split something up using electricity, and for that to happen, ions need to be able to move. But in a solid ionic substance, so in a crystal, a giant ionic lattice as we call it, the ions are fixed in place by strong electrostatic forces, and they can't move. All they can do is vibrate. And if the ions can't move, then charge cannot flow. Okay, so I'm going to say that ions are fixed in place in an ionic solid, so therefore cannot move and charge cannot flow. Right, in order for it to flow, you'd have to either have an aqueous solution of the potassium salt or a molten liquid potassium salt if you melt it. All right, because then the ions are free to move and charge will be able to flow. Okay, so part 2. It says that Humphrey Davy was the first person to produce potassium. His experiment to produce this new element was quickly accepted by other scientists. Suggest why. Okay, and normally questions say why wasn't something accepted, but here it says that it was accepted. Okay, so think why. Well, there are 2 real reasons. The first one will be that because he's produced it, he's got evidence to show that he has produced the element potassium. So I'm going to say that he had evidence. That's bad handwriting. Let's rewrite. Evidence to support his claim. Right, his claim. And that would be more than enough for 1 mark because it's only a 1 mark question. Another mark could have been from saying that he was a professor of chemistry, right? He had status, he was a scientist, and so people would accept his ideas. The common one, if you're taking the biology exam as well, is that Gregor Mendel was a monk. He wasn't strictly a scientist, and so people didn't accept his ideas as quickly. Okay, that's going slightly off topic, but it's an example of why people wouldn't accept ideas. All right, so 4b, it says a student dissolved some potassium chloride in water. The student tried to electrolyze the potassium chloride solution to produce potassium. The apparatus the student used is shown in this diagram. Alright, so we've got a positive electrode, negative electrode. They are joined up and we have a power supply here. And we have potassium chloride solution in which the electrodes are submerged. Alright, and so let's turn over and have a look at the question. It says the student expected to see potassium metal at the negative electrode, but instead saw bubbles of gas. Name the gas produced and explain why the gas was produced and why potassium was not produced. The reactivity series of metals on the datasheet may help you to answer this question. Alright, and now you should know that if a metal is really reactive, okay, and you have a solution, the solution is going to be dissolved in water, and so you also have H+, I'm just going to write that up here, you also have H+ and OH- ions, alright? So in aqueous solution, you've got those ions as a result of water. Now, if a metal is more reactive than hydrogen, then hydrogen is more likely to be produced at the electrode. Reason being, because if something is really reactive, it doesn't want to become an element. It wants to react and stay in solution, because in solution, it's reacted and forms a compound. So, what I'm going to say first of all is that hydrogen gas produced, and that's a result of these hydrogen ions, okay? They're less reactive than potassium, and so they produce hydrogen gas. Okay, secondly, we need to explain why the gas was produced, okay? So, H+ ions were attracted to the negative electrode. Here, they accepted electrons. Let's neaten that up. Electrons to form hydrogen. Okay, and now we need to say why potassium wasn't produced. Potassium stays in solution as it is more reactive than hydrogen. Alright, and that would be worth the 3 marks. So next, we've got 4C. The student tried to electrolyze molten potassium chloride to produce potassium. Potassium metal was produced at the negative electrode. Describe how potassium atoms are formed from potassium ions. Alright, so this time it's not in solution, so you don't have hydrogen ions. So all you can produce at the negative electrode are the potassium atoms, right, from the potassium ions. Okay, so potassium ions gain an electron. Okay, potassium is in group 1, so it has +1 ions. They only need to gain 1 electron. So potassium ions gain an electron each and form potassium atoms. Okay, alright, let's move on. C part 2, it says complete the balanced equation for the reaction at the positive electrode. Alright, well at the positive electrode, you're going to get chloride forming chlorine. The way it does that is it donates its electron, okay? So if a chloride ion donates its electron, it forms a chlorine atom. But because chlorine doesn't like to exist as atoms, it likes to exist as molecules, that's why we have 2 of them, right? So we need 2 chloride ions to balance that out. And now if each one of those chloride ions gives away one of its electrons, that gives you a total of 2 electrons that it's given away. So what you produce is chlorine as a molecule and 2 electrons. And we write that 2E-. Okay. Then it says complete the diagram to show the electronic structure of a chloride ion. Okay. Now if you take a look at a periodic table, you'll know that chlorine will look something like this. You'll have 35.5 at the bottom and 17 on the top. What's important is that 17. That tells you the number of protons and thus the number of electrons in a chlorine atom, okay? In an atom, so that's important. In an ion, chlorine accepts 1 electron to become chloride, and so the number of electrons is going to be 18 electrons, all right? And so what we're going to do is we're going to draw chlorine. We're going to write Cl in the middle. And we are going to fill up the energy levels, okay? I'm going to use crosses to show electrons. And the first energy level can hold 2 electrons. And after that, the next 2 energy levels, can hold 8 electrons each, okay? And the most correct way to do it is to draw them in pairs, like so. But you would not be penalised for drawing them evenly spaced out. But in pairs is the best way to do it. Now, we now have 7 on the outer shell. This would have been a chlorine atom. So a chlorine ion is going to have 1 extra. And I'm going to actually draw that as a dot, okay? Because that electron has come from somewhere else. So that means that drawing it as a dot shows that that electron is foreign and it's come in. Okay? You wouldn't, because it doesn't tell you to draw a dot and cross diagram here, you wouldn't be penalised for just drawing it as a cross. But the more correct way to do it is to draw a dot like that, because that shows that that electron has come from somewhere else. All right, but either way, you would have got that mark. Okay, so moving on, we have question 5. So question 5 says that oil rigs are used to drill for crude oil. Drill heads are made from steel, and steel is an alloy, right? That's true. Explain why alloys are harder than pure metals. Well, if you think about the arrangement of metals, in metallic bonding, you have layers of metals like so. So those are the atoms, which actually then become ions because electrons are delocalized, right? So all of those little dots are positive metal ions, okay? The thing is that those ions or atoms, depending on how you want to think about them, they are all the same size if it's just one pure metal, and so these layers can slide over each other. But what happens when you start to introduce bigger and smaller ions or atoms? Okay, now the layers can't move over each other because the sizes are different, and it stops the layers from being able to slide. Okay, And so that's what we're going to write. So we're going to say that ions, I'll put in brackets there, atoms are different sizes, and so the layers are no longer regular. Okay, by that I mean that, all the sizes are not the same, and so the layers themselves are distorted or they're not regular, right? Okay, this means that layers therefore cannot slide over each other. Let's make that a bit clearer. Over each other as easily. Alright, and that makes them harder. Okay, so that's more than enough for those 3 marks. So moving on, it says that drill heads also contain diamonds. Describe as fully as you can the structure and bonding in diamond. Alright, and so the first thing you're going to write is that diamond has a giant covalent structure. Okay, full stop. So that's 1 point. It's made up of carbon. Okay, each carbon is bound to other carbons by strong covalent forces or bonds. Alright, and now I'm finally going to say that each carbon is bound to 4 other carbon atoms. Alright, and so that's more than enough for all the marks there. So it's a giant covalent structure made up entirely of carbon, okay? Strong covalent bonds bond the carbons together, and each carbon is bound to 4 other carbon atoms. Alright, so next it says that polymers are produced from crude oil. Describe the structure and bonding in a thermosoftening, let's underline that, thermosoftening polymer, and explain why thermosoftening polymers melt when heated. Alright, so thermosoftening polymers, well, the plastics or the polymers that you get from crude oil are made up of hydrocarbons. Okay, so I'm going to say large hydrocarbon molecules make up the polymer. Okay, I'm going to say that the molecules are bound together by covalent bonds. Okay, I'm going to say there are no covalent bonds between the molecules. Okay, so there are no covalent bonds bonding one molecule to another. Covalent bonds are only found within each molecule. Okay, so between molecules. Okay, weak intermolecular forces exist between the chains, or the molecules, between molecules, which are overcome by heat, causing the polymer to melt. All right. So the point there is that in order to melt a thermo-softening polymer, you don't need to break any covalent bonds, you just need to break the intermolecular forces. If you were to melt something like diamond, which is not going to happen, you need to break all of the covalent forces, because that is what is holding the whole structure together. Whereas the things which are holding the molecules together in the thermo-softening polymer are the weak intermolecular forces, not the covalent bonds. They are holding the molecule itself together. Alright, and that's the end of question 5. So let's move on. Right, so question 6 says that spacecraft have been to the planets Venus and Mars, and the spacecraft have sent back information about the atmosphere of each planet. The main gas in the atmosphere of Mars is carbon dioxide. Explain why, in terms of structure, carbon dioxide is a gas even at low temperatures. Now, this is similar in terms of the explanation to the last question, but obviously plastics are not gases at room temperature. So carbon dioxide consists of simple covalent molecules. Alright, full stop. So simple covalent molecules are what make up the carbon dioxide. So these have weak intermolecular forces to each other. Alright, these forces are easily overcome at low temperatures. Oh, that's terrible. Low temperatures. I'll make that a comma. So molecules can easily move as a gas. Or I'll say they are free to move as a gas at those low temperatures. Alright, and that is the 3 marks. And moving on. Question B, it says gas chromatography linked to a mass spectrometer is used to identify substances found on Mars. What is the purpose of gas chromatography? Well, chromatography doesn't actually identify anything outright. You would have to compare it to other things to be able to identify. But what chromatography does do really well is it separates things. So this is to separate different substances. Alright, now it says, what information do the molecular ion peaks from the mass spectrometer give about the substances? Now, important there, it says molecular ion peaks, and those are the large peaks at the end or the far right hand side of a mass spectrum. And what they tell you is basically the molecular mass. Alright, so they tell you the relative molecular mass. Alright, C. It says the atmosphere on Venus contains droplets of sulfuric acid solution. Now it says suggest a pH value for sulfuric acid solution. Now that would obviously depend on the concentration of the sulfuric acid. Important is that you say it's below 7 because 7 is neutral and acid has a pH below 7. I'm going to say something like 2 because sulfuric acid is strong, but if it was a dilute solution then it might not be a really, really low pH, so I'll just say 2. That'll be fine. Name the ion which makes sulfuric acid solution acidic, and that is the hydrogen ion. Okay, so hydrogen ion, and I'm also going to write H+. Okay? Alright. In D, it says the atmosphere of Venus contains the isotopes of hydrogen, so these are 2H and 1H. Alright, that just tells you the size of them. Describe the similarities and differences in the isotopes of hydrogen. You should refer to the subatomic particles in each isotope. Okay, so subatomic particles, bearing in mind this is a 3-mark question, the subatomic particles are the proton, the neutron, and the electron. Okay, so what I'm going to say is that H1 has one proton and one neutron. And no neutrons. Okay, because it has a proton number of 1 and a mass of 1, which means that there is no neutrons on there. And the hydrogen with a mass 2 has 1 proton. Right, I'm going to write also here actually. Make it a bit more clear. Also has 1 proton because that shows it's a similarity. But has 1 neutron. Alright, so the amount of neutrons is different because this one has a mass of 2 but only 1 proton. So that other 1 unit of mass must come from the neutron because electrons don't have a mass. Okay, or they have a tiny mass which we don't care about. Okay, number of electrons though. Bearing in mind that isotopes are the same element, both of them are going to have 1 electron. Okay, so number of electrons is the same. And that equals 1 electron. Alright, and that is good enough. And that is actually the end of this entire test. Okay, and so I hope you are able to follow that. If you do have anything you need to go back on, please feel free to rewind and pause the video. But if you do have any questions on top of what we've covered, please feel free to post them in the comment box below or send me a direct email using the link in the description and I'll be sure to get back to you. But please do like and subscribe and share this video as usual because it really does help me out and I can make more and more videos in the future and so you'll be notified of those. But thanks for watching and I look forward to seeing you in the next one.